All right. So chapter 5 is not going to be that different from chapter 4. Okay, it's technically a new proof technique, but it's all going to boil down to do this and then do direct proof. Okay, so it's not going to be that different. It's all going to rely on using the contrapositive of a statement. Does anyone remember what the contrapositive of P implies Q is? Yeah, not Q implies not P. What did we say about a statement and its contrapositive? They are equivalent. They have the exact same truth value. Okay, so if one of these, if I can show one of these is true, then I know the other's true. All right, so let's practice writing contrapositives. My favorite, if it's a dog, then it's a mammal. What's the contrapositive? Yep, if it's not a mammal. Then it's not a dog. All right. The next one, we got to be a little careful. If a number is prime, then it has exactly 2 divisors.
It could be like if a number has more than 2 divisors, it's not prime.
Okay, so if a number has more than 2 divisors, it's not prime.
Or use that other definition.
No, but that works for almost all cases, but what's the one thing that leaves out? 1. 1 has 1 divisor. So the opposite of exactly 2 divisors is going to be it has 1 divisor or lots of divisors. Okay, does that make sense? 1 or more than 2. Yeah. So when you write this, you're going to say if a number has 1 or more than 2 divisors, then it's not prime. Okay. Why can't I change not prime to composite? Because of silly old 1 again. Okay, so composite is not the opposite of prime because that number 1 messes things up, just like positive and negative aren't negations because of 0. Okay, so all right, next one. If A times B is even, then A is even or B is even. What's the contrapositive going to be?
Or B is odd.
Yeah, so I heard it somewhere in there. So what happens to an or when you negate? And so if A and B are odd, okay. If A and B are odd, then AB is odd. All right, any questions on those 3 statements? Okay, so the first proof I want to do is going to be on that one we just did, right? So if I want to prove if AB is even, then A or B is even, that would actually be very difficult from that standpoint. But if I use the contrapositive, which is A odd and B odd, implies AB odd, then the proof becomes much easier. Okay, so let's think about why this would be easier. the first way, if I did a direct proof on the original, I'd have AB equals 2K. Well, how do I figure out that that 2 has to go to A or has to go to B? That's not just a straight follow the algebra type thing. This second way, though, the contrapositive way, we're just going to be able to use the definition and follow algebra. In fact, I'm not even going to write scratch work. Okay, so proof. By the way, you're allowed to abbreviate the word proof PF if you want. Suppose A and B elements of the integers. So A and B are integers with both odd. All right, here we go. Just like chapter 4. Then there exist, I'm going to call them K and L in the integers such that A equals 2K plus 1 and B equals 2L plus 1. Note that, here we go, let's do our algebra. AB will equal 2K plus 1 times 2L plus 1, which is 4KL plus 2K plus 2L plus 1. And I'm wanting to get odd. I'm wanting AB to be odd. So I need to write it in that form. 2 times something, which is 2KL plus K plus L. All that plus 1. Yep. So since 2KL plus K plus L is an element of the integers, AB is odd. Okay, technically at this point, we could just stop and be done and put our box. I'm going to add one more line since we're doing the contrapositive method of proof, just to be super specific. So I'm going to say, therefore, by contraposition, yeah, make you sound all smart and fancy. Contraposition, if AB is even, then at least one of A or B is even. And now I'm going to put the box. Again, technically that last line is not necessary. In fact, in upper level math, they'll often do a proof by contraposition and they won't tell you that's what they're doing. They just expect you to be able to look at it and figure it out of, oh, they proved the contrapositive. Okay. But for our purposes, right, we're just learning. It helps to kind of state this is the method I'm using. Okay. All right. What questions do people have in that one? Okay, so let's look at another one where contrapositive is going to help. And this is just such a good one. I am doing one of the book examples. Oh my. Okay, so let X and Y be integers. Prove that if 5 doesn't divide the product, that 5 can't divide either one. That's what it says. So if I tried to prove this directly, don't write this because I'm going to erase it. I'd have to figure out what 5 doesn't divide XY means. Well, that means for every K, because it's not a there exist, right? XY does not equal 5K. That's kind of hard to work with, okay? So here's where we go, if I negate these statements, my doesn't divide are going to become does divide, and that I can work with. So that's what gives us a hint. Contrapositive could be helpful here. So what is the contrapositive of this? Well, let's see. My hypothesis is going to become my conclusion when I negate. And my conclusion will become hypothesis. What happens when we negate an and? Becomes an or. So this becomes 5 divides x or 5 divides y implies 5 divides xy. That's much easier to work with. Okay. All right. So we can do a little bit of scratch work. You may be able to do this one without scratch work, but let's do it. So if 5 divides x, if I'm in that case, that means x is 5 times some integer k. And I want 5 to divide xy. What can I do to get 5 dividing xy? What can I do to that equation? How can I get from x to xy? Multiply by y. That's all you got to do. Don't overthink these, guys. And that'll work because y is an integer, so k times y is still an integer. What about the other case with 5 divides y? It's going to look exactly the same. I'm just going to multiply by x in the middle. So I have a choice. I can use without loss of generality, or I can use similarly, or I can write out both cases. I'm going to use without loss of generality. Okay, so here we go. Proof. Let x and y be integers such that 5 divides x or 5 divides y. WLOG, without loss of generality. Assume 5 divides x. All right, then there exists k in the integers with x equal to 5k. But this means xy equals 5 ky. Since the product of integers is an integer, right? I'm trying to show you the variety of ways you can say the same thing. Since the product of integers is an integer, ky, element of z, ky is an integer. Thus, 5 divides xy. Again, at this point, we're done. We could technically add another sentence that says, therefore, by contraposition, blah, 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 and state our original. But technically, we're done here, okay? So what you should notice here is every single time you prove something that's a conditional, you actually get 2 statements that you've proven. All right, so we get 2 usable facts from each theorem we prove. Original and contrapositive. So we've proven what, if A and B are even, then their sum is even. So that means technically we've shown that if the sum is odd, then at least one of A and B is odd, okay? Because we've shown the contrapositive, we get the contrapositive for free once we've shown something. Any questions on that page before we go to the next page? Okay, next page. All right, so another example. Oh, why do I have two equal signs? That's bizarre. Let's cross one of them out. Yep. It's called me editing the notes in a hurry. Okay. So prove that if x plus 1 squared is not equal to x squared plus 1, then x can't be 0. Again, I have not equal. That's hard to work with, right? But if I take the contrapositive, those nots become is equal, and that's way easier to work with. So let's write our contrapositive. So our contrapositive will be x equals 0 implies x plus 1 squared equals x squared plus 1. I'm not even going to write up scratch work before I write my proof, because literally I'm assuming x equals 0. So I'm literally just going to plug 0 in. Okay, so let me show you how that'll look though in the proof, because we got to be careful. All right, so proof. Let x be an element of the reals with x equals 0. Then x plus 1 squared equals 0 plus 1 squared equals 1. But x squared plus 1 equals 0 squared plus 1 equals 1. So x plus 1 squared equals x squared plus 1. Done. Again, you could add the statement. So by contraposition, if x plus 1 squared is not x squared plus 1, then x is not 0. You could write that statement in.
The whole repeating themselves like that every time you write a contrapositive proof is why they don't do that.
Yeah, I mean, mathematicians like to be very to the point and not too wordy. And so as you get more and more comfortable with proofs, you write the proof to kind of where you are, to what your audience you would expect to be at your level. So as the mathematician gets more and more advanced, the proof gives less and less and less detail and justification of stuff like this, because they assume their audience already knows that and move on. Okay. Now, this isn't the only way you could prove this one. You could have gone about this one if you wanted to do a direct proof by squaring out that side, saying that does not equal x squared plus 1, and arguing that that extra term, if x were 0, that extra term wouldn't be there and you'd get it equal or something. But that's a lot weirder. That's not as straightforward, right? So contrapositive makes this ridiculously easy. Okay, cool. So now we have an important definition that's definitely going to come up for you math majors. It'll come up again, definitely in Math 465, possibly in some other ones. Okay. So this A, little triple symbol B mod N, this we call A congruent to B modulo N. And I'm going to tell you what that means. Okay. So that's how we say it out loud. When I write those symbols, I'm going to say A congruent to B mod N, or A congruent to B modulo N. Okay. The idea of modulo arithmetic here is I'm wanting to relate things based on the remainder when you divide by N. The technical definition looks like this: N divides A minus B. Okay. So let's look at some examples. So for example, 7 is actually congruent to 4 mod 3. Okay, because 7 minus 4, well, that's 3. 3 definitely divides 3. Let me do another one. 22 is congruent to 4 mod 3. Because 22 minus 4 is 18. And 3 does divide 18. Oops. All right. So what is 7's remainder when divided by 3? 1. What's 4's remainder when divided by 3? 1. What's 22's remainder when divided by 3? 1. That's why they're all congruent, mod 3. Okay. If you take two things that have remainder 2 when divided by 3, they should be congruent. So for example, what would have remainder 2? 14 and 11. And yeah, those are 3 apart. 14 minus 11 is 3. Okay. Yep. So does that make sense how modulo is working? So give me two things that are congruent mod 5. Any two natural numbers congruent mod 5, or integers. You can use negatives too. 25, what would it be? What's something 25 is congruent to mod 5? 5, yep. Any multiple of 5 is going to work, right? Because when I subtract those, it'll still be a multiple of 5. They both have 0 remainder when divided by 5. Okay, that's what we mean by modulo. Okay. Another example, I don't know. If I took 18, it would be congruent. So that has what? Remainder 3 when divided by 5. So that would be congruent to 33 mod 5. Because 18 minus 33 is negative 15. And 5 does divide negative 15. Okay. All right. So that's modulo. That's the idea of it. Let's see how it works in a proof. So here we go. We want to give a direct proof to show if A and B are congruent mod n and C and D are congruent mod n. Then A plus C is congruent to B plus D mod n. Basically what we're wanting to get at here is I can kind of treat that congruent like an equal sign and say, well, I added the same thing to both sides in a sense. Okay, you see that if C and D, I'm considering them the same thing modulo n, I can add them to each side and I won't mess it up because they're considered the same modulo n. All right, that's what this one is saying. So let's go ahead and do scratch work on this one. So A congruent to B mod n and C congruent to D mod n. Like with all these proofs so far we've done, you go back to the definition. My definition, this means n divides A minus B. And this means n divides C minus D. All right, but now I have another definition to use because I have to remember, what does divides mean? Well, that means A minus B is n times some integer k, and C minus D is n times some integer L. Move this up. So let me remember what my goal is. My goal is A plus C congruent to B plus D mod n, which will mean n divides A plus C minus B plus D, which will mean A plus C minus B plus D equals n times some sort of integer. Right, so again, I'm using those exact same definitions. I'm just starting at bottom, writing to the top because that's my conclusion I'm wanting to get to. Yeah.
How do you get from the goal to that second to last step?
So I just use the definition of modulo n, right? If the left side's going to be congruent to the right side, modulo n says that means n divides left minus right. So that's all I did. N divides left minus right. Yeah. Yep. All right. Anyone see how I can get how I can connect the gap between the two parts? Yeah, so you actually don't even have to solve for A and C, but your idea of just add them together, right? Because this is A plus C minus B minus D. Everybody see that? A plus C minus B minus D. If I add these two equations together, I get A plus C minus B minus D equals NK plus NL. Well, that is A plus C minus B plus D equals N times K plus L. And that's what we needed. So that's your scratch work. Then you pull out your nice clean paper that you're turning in for your homework, right? And write up your proof. By the way, come the midterm and final exam, I'll sometimes ask a question where I say, just show the scratch work for this. Don't write up the proof. Okay, so that is also a possible question, is just do the scratch work. So, all right, here we go. Proof. Suppose A congruent to B mod N and C congruent to D mod N. Now, you can write in both steps we have here that, okay, so the definition of modulo means N divides these. I'm okay if you also skip that step straight to our next step of our scratch work and say, thus, there exist K and L in the integers with A minus B equal to NK and C minus D equal to NL. It's up to you if you want to put that middle step between those or not. Okay, that's fine either way. Again, this is kind of a, you're assuming your audience is about your level. Okay, so, all right. So we have C minus D equals NL. Now what did we do? Oh, we added them together. But adding these together gives, and here we go, A minus B plus C minus D equals NK plus NL, which is A plus C minus B plus D equals N times K plus L. All right. Since K plus L is an integer, N divides A plus C minus B plus D. But by definition of modulo, A plus C is congruent to B plus D mod N. In my class, you can. Yeah, sorry, I didn't realize I did that. This DEFN, that's an abbreviation I made up when I was taking lots of math classes and tired of writing the word definition. You're welcome to use it in my class. I don't know if any of your other teachers would know what that means. Okay. Yep, I didn't even notice I did that. I'm in such the habit of it. All right. What questions do people have on that one?
So we just say like definition of a modulo, another one. Oh, so when you say that, you can just say modulo.
Yeah, that's fine. If you say definition of modulo, or I could have said of congruence modulo n, if I wanted to be more formal. By definition of congruence modulo n would be the super formal way of saying it. Yeah. Other questions on that? All right, so let's look at another proof involving modulo. Now on this one, I'd has used proof by contraposition to show n does not divide m, implies m can't be 0 mod n, or m is not congruent to 0 modulo n. Why is contraposition a good idea here? Yeah, those knots in there when I negate are become it is. So we're looking at m congruent to 0 mod n implies n divides m. We hardly have to do any scratch work on this one, so I'm going to move to the side, but we're going to hardly write anything. Okay. If m is congruent to 0 mod n, what's the definition tell me that means? N divides m minus 0. But what's m minus 0? M. And that's the conclusion we want. So this is going to be a short proof. One-line proof is sometimes what you hear them called when it's that ridiculously easy. So proof, assume m is congruent to 0 modulo n, then n divides m minus 0. So obviously n divides m. Done. Best kind of proof right there. Yeah. So. Obviously. Okay. All right. Any questions on that one? Cool. Next page. So here we have some more examples, but this time we're just going to set up the proof. Okay. So we're going to set up the proof in two different ways. We're going to see what it would look like if it was direct, what it would look like as contrapositive. Okay. So direct, and then we'll do CP for contrapositive. All right. So my statements, if a squared is odd, then a is odd. If I were going to do a direct proof, what would I assume? A squared is odd. And then I'd work from there, blah, 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 blah. And what would my goal be? A is odd, yeah. Which, yeah, would be the same thing as saying A is 2k plus 1 or something like that. Okay. What if I was going to do this proof by contrapositive? What would I assume? Yeah, assume A is even. And then you do work, blah, 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 blah. And what would your goal be? A squared is even. Okay. All right. In fact, now that we know modulo, there's a stronger fact I can make about this. If A is even, when I square it, it's not just even, but what does it have as a factor? So A has 2 as a factor, so what happens when I square it? It's going to have 4 as a factor, right? It has 2 2s. So A squared is actually 0 mod 4 because it's divisible by 4, actually. Not only is it divisible by 2, it's actually divisible by 4. Interestingly enough, if you have an odd, this may be one of your homework problems or it's a book example. When you square it, it's actually going to end up being 1 mod 4. So when you square a number, you'll never get 3 mod 4 or 2 mod 4. It'll only be 1 or 0. So that's kind of cool. Anyway, random fact. Okay, let's keep going. Next one. Well, quick comment on that though. Which one of these proofs seems like it would be easier to do? The contrapositive would be way easier. Okay, the contrapositive is the better approach here, because if A is even, A is 2k squared, is 4k squared, move from there. Okay, the other one, that's a little tougher. Okay, all right, next one. I'll give you a head start. So set up the direct, set up the contrapositive. All right. So those are what you should have. Direct, you have the not congruence, right, in the original order. Contrapositive, you negate it, so not congruent becomes congruent. And then you've switched the order, okay? Which one of those seems like it'd be easier to approach? Contrapositive by far, okay? The proof for this one, well, I don't know if that's a homework one or not, so, but it comes down to when you do the a squared minus b squared, you have to factor it and consider how it factors and stuff, so. Okay. Next one. So this one is not a if-then type thing. For direct or contrapositive, this setup, we need to figure out how we would approach this proof. If I want to show for every natural number 4 divides that mess, what might be a good way to kind of split this up? Any ideas? What's a good way to split up natural numbers, maybe and do in cases? Odd or even. That's actually what would work for this one. Because if that in, you plug in 2k or 2k plus 1, it gives you something to work with. So this one, the setup, you know, you'd say assume n is in the natural numbers. Case 1, n is odd, blah, 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 blah. Case 2, n is even, blah, 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 blah. And then somehow out of that, we would get our goal that 4 divides that crazy mess. Okay. So typically, if I put a set up the proof on a test or quiz, I'll tell you if I want you to set up the direct or the contrapositive, or if I want you to set up cases or something like that. I tell you what I'm going for, okay? And I'm just wanting to see, do you know kind of the format it would take without any details in it? All right, any questions on that one? Okay, so the book in section 5.3 has some really nice comments on proofs. They're just generally accepted grammatical practices. So for example, when you start a sentence, you should start with a word, not a mathematical symbol. So if you're wanting to start by saying for every X, you cannot start the sentence for every X. You would actually have to write out for all, X and R or something. Okay. So that's just proper grammar. You cannot start with the symbol. Okay. No. Yes. Okay. But if it's in the middle of the sentence, you're perfectly fine to use the symbol. Okay. All right. End each sentence with a period. You'll notice in some of my proofs, when I have those strings of equations, I still put a period at the end. It's because as I'm saying it out loud, that is the end of my sentence. Note that X plus 1 equals this, X equals this, therefore X equals 7, period. Okay, those string of equations, I put a period at the end. So every sentence ends with a period. Separate math symbols and expressions with words. Your proof should not just be an entire string of symbols. Okay, remember, this is a story you're writing or an argument to a jury you're writing. It needs connecting words and everything in between it. Okay. Avoid misuse of symbols. The most common ones I see would be people wanting to say an integer plus an integer is an integer, something like that. And they write integer plus integer is an integer. That's nonsense. You're saying the set of integers plus the set of integers is the set of integers. That's nonsense, right? So that's a misuse of the symbol. That Z symbol means the set of all integers. It is not a replacement for the word integer in your language. Another common one is A divides B. This is a phrase, and yet I'll have people put it in the middle of an equation. No, this isn't a number. This is a phrase. It can't go in the middle of an equation. Okay, so just be careful with your symbols. Or if you're writing the word subset, you can say X is a subset of Y is fine. Saying X is a subset of Y is not fine. Okay, is this kind of making sense with symbols? Okay, cool. But if you can avoid as much as possible, and you'll learn, like I said, you're learning a new language here. So, I mean, when you were in, kindergarten, first grade or whatever, writing stories, and you misspelled a word, your teacher just said, nice story, by the way, this word's misspelled, right? That's what I'm going to do, okay? Okay. Avoid using unnecessary symbols. That, what's a good example? So, yeah, if that would be like saying, you're saying real number, X and the real numbers. It's kind of like you already said it's a real number. Why are you again putting it's a real number? Okay, unnecessary symbols there. Okay, all right. Oh, this is great. This would make your English teacher cringe. Okay, use the first person plural. When you're writing your proof, you're like, we're gonna do this. This is, and our equation shows, right? Bring your audience in. They're working with you in this, okay? And you use the active voice. You say, now let's divide by 3, okay? That together, that's mathematical style. Your English teacher has told you, never do that, right? That's completely wrong. In math, that's what we want. It makes the proof more interesting, and you want the proof to be something your readers going through with you feels like they're going through the steps and the logic with you. Okay, that's what you're going for. Explain each new symbol. For your reader's sake, if you are introducing something that's not commonly used, you need to say what it means. Every symbol we've learned so far is commonly used. Okay, but if you're making up your own symbol for something, or if it's kind of an obscure symbol you found, you better say what it means, okay? Or your reader's going to be lost. I've had that before. Normally that happens when people look stuff up on the internet and the internet person uses certain symbols and person just copies it. I'm like, what's that symbol mean, right? You got to tell me. Okay. Watch out for it. That is just because of the ambiguity. So let's say you have a sentence about a number A and a number B, and then your next sentence starts it, da da da. Say, wait, are you talking about A? Are you talking about B? Are you talking about something else? So be very clear as to what you're discussing. Okay. And then it just lists some nice synonyms so your proof isn't using the same words over and over. Okay. You know, since, because, as, for, so, thus, hence, therefore, consequently. I also like ergo, right? All that. All good words. Then, I use then a lot. Okay. Try to get a little variety in there in your proofs. And then this is the big one, number 12. Clarity is the gold standard of mathematical writing. I love the way the author said that. It's very clear. Mathematicians are not about being verbose and flowery. You'll hear sometimes people talk about a mathematical proof being beautiful. Oftentimes that doesn't mean like a poem, they wrote it, using beautiful language or imagery or something. Normally for a math, a proof being beautiful means maybe they used a clever idea, but the way it's explained is just so clear and so simple. I remember in grad school, my combinatorics class sitting there, and one day the professor put up this theorem and we're all looking at it going, I have no clue how you're going to prove that. And then he just stands back and goes, let's pretend we're painting the floors of a building, and then proceeded with the proof, and it all just fell together perfectly, made perfect sense. That's a beautiful proof. Okay. Yeah. So dissertations and stuff for math, there's no length requirement to it like there would be in history or English, because it's all about the clarity and the logic. It's not about the floweriness or the verboseness or anything like that. Okay. So, and each of you are going to develop different levels, of how terse you are and how wordy you are, and that's fine. Proofs kind of become your own. So